So the last time we met, we looked at the fractional programming problem. And this is a fractional programming problem. At each point in time, when you don't understand something, let me know. Let me know. Let me know by either raising your hand or unmuting yourself and asking. Because I have put everything on a recording and a screen. And so I wouldn't want a situation where anybody, I wouldn't see what you are saying if you type. I wouldn't see what you are saying. I wouldn't see it. So it's important that you sometimes have to unmute yourself and ask the question. All right. So this is the linear programming problem. This is it. The output oriented. And in the multiplier form, the multiplier form, the weighted sum of the output is set to 1 for output oriented. The weighted sum of output is set to 1 for output oriented. And in the input oriented, the weighted sum of the inputs is set to 1 for the input oriented. The weighted sum of the input is set to 1 for the input oriented. For the output oriented in the multiplier model, you have minimized. But for the input oriented, you have maximized. Now, you will not be using much of the output oriented. You will not be using it much. Okay. And so we will not be talking much about output oriented. So about the multiplier. So we're going to focus more on the linear program, the envelopment model. And if you have done a bit of linear programming, you know that every primal model has got a dual version. Okay, you have the primal, you have the dual. And you can use that concept of duality to actually correct the primal and the dual. You can use the concept of duality to actually handle it. All right, so try and explain the output-oriented envelopment model that you see on your screen for them.
Okay, so it's the phi here. The phi signifies like is the symbol for the efficiency, the output efficiency. So we are maximizing the output efficiency subject to these constraints. The first constraint says that the weighted sum of all the inputs is less or equal to the inputs of the DMU under evaluation. And then the second constraint is that the weighted sum of all the outputs is greater or equal to the output of the DMU under evaluation. Now the phi is attached to this constraint, the Y here, because we are looking at output orientation. And then, Doc, please, can you scroll up a bit? I can't see the VRS. Okay. So the next constraint is the VRS. But if you are doing it under CRS, this constraint where the weighted sum, the sum of all the weights is equal to 1 is dropped. And then we have the non-negativity constraint, please.
Put a limit, like an upper bound on the weight of the DMUs. Okay, so the summation of all the weights must be equal to 1. That is 100%, which is more or less, you are saying that this is the upper bound, which you can't have more than that upper bound, that's 1. So in essence, it helps us to... Please come again.
How is that different from the CRS? Let's go.
The objective function, the phi that we see here, stands for the technical efficiency, the efficiency when we are dealing with output orientation. We all know that if it's input, it would have been theta. So this is the phi for outputs. And the objective function is to maximize the weighted sum of the phi, to maximize the technical efficiency here, subject to certain constraints. So the first constraint says that the weighted sum of...
Hold on. So why is it that under the maximize, you have the lambda and you have the theta? What is the purpose and what are they for?
Okay, so I know that we are maximizing the weights. We are maximizing the weights of Doc, can you please help us?
No, I'm trying to see how you go on. So you go on.
Okay. Okay, so subject to. The first constraint says that the total sum, the weighted sum of all the inputs of all the DMUs should be less or equal to the input of the DMU and the evaluation. And the input here is I, the I is equal to 1 to M. M is the total number of inputs being used. So if it's 3 inputs, it means that you're going to have 1, 2, and 3. 1 to 3. If it's 2, 1 and 2. Then the second one says that the weighted sum of all the outputs of the DMUs, of all the DMUs, should be greater or equal to the output of the DMU and the evaluation. So R here is the output and it ranges from 1 to S. S is the total number of outputs being used. Now I said that we attach the phi to this constraint, the right-hand side of this constraint. That's the second constraint because we are dealing with output orientation. If we were doing input orientation, then the theta would have been attached to the first constraint, the right-hand side of the first constraint. Then the third constraint says that the sum of the weights should be equal to 1. That's for VRS. And then the weight should be non-negative. And J here is equal to 1 to N. N, that's the number of DMUs. J is the number of DMUs being 1 to N.
Okay, thank you. So guys, I want you to understand this is an output-oriented model, which means that if you are dealing with a bank, the goal for using this model is when you believe that the banks are aiming at increasing all the outputs at the same time. The outputs may be loans and advances. You may have output like investments. You may have output like off-balance sheet activities or CSR. Now, the goal is to increase all these outputs, given the input. So you are not going to reduce the inputs, which are labor. That is the number of employees or staff cost. Capital, where capital here might be standing for shareholder funds, financial capital, or physical capital. If it is physical capital, then we are talking about something else related to fixed assets. So that's it under the condition. If it was an input-oriented model, then your goal would be to reduce the labor, reduce the capital, reduce the deposit. But in this context, we are keeping all of these constant and then we are increasing the output. That is where you use this model. Now, to increase it, so the whole idea is that you are going to maximize theta. So there's a variable called theta, and you are using that theta to maximize the output. Now remember, in an output-oriented model, you have something like this. Watch what I'm about to show you now. You have something like this. So I'm just drawing a kind of a model where you have y1 and then y2. And then the output-oriented model is something like what you see on your screen. And then you have a variable which is say output y11 and then output y22 here. And then the variable is there. The DMU is here. So this DMU will have these outputs, which are, let's put it together. I call the coordinates of the output to be maybe 4 and then 4. And this DMU, let's call it DMU A. This DMU A is inefficient. And we know it's inefficient because it's not on the frontier. And our goal is to move it towards the frontier, okay, in the direction of the origin. So I'll start something like this from the origin, pass it here, and then until I move it to that angle there. So I move the thing to the origin. I move the thing to the origin. I move it to the origin. Now, how do I move it from A to the origin? Let's call it A prime. How do I move it from A to A prime? Now, I need something to help me to move it there. Now, when I say move it there, what I mean is that I'm increasing this 4 and increasing this 4. Because as you move along the radial line, you are moving it towards the origin. I need something. I need something. I need something that will help me to move them from 4, 4 to maybe the value at the top here, 8, 8. What do I need? Theta is that thing. Okay. Well, in this case, it is phi because we are dealing with output oriented. So you need phi. Phi is that thing. Phi is that variable that will help me to move this coordinate to the target, to move these actual output to the target output. Phi is going to help me. So if I multiply the phi by the 4, so that I have 4, 5, and then another 4, 5, I can now move these 4 to the target values of say 8. The question now is, how do I get a phi? And that is the essence of the linear programming. So the linear programming is saying that if I get the phi, it becomes phi star. So now let's go back to the programming. So when you come to the programming here, you see that the goal is to get the actual value of phi, which is the phi star. Now, for me to do that, I need to maximize. What am I maximizing? Because I'm moving the phi to the origin, to the frontier, the boundary. I am moving this phi, and my goal is to get the value of the actual phi. So the values you see here, the phi here, is something I am looking for. In a linear programming, there's that kind of decision variables that you are looking for. Do you remember? So this is my decision variable I'm looking for. The lambda is also a decision variable that I'm looking for. But it just happens that the phi is also an objective function. Okay, it's a decision variable, but it's also an objective function. But the lambda is only a decision variable. Now, why do we say it's a decision variable? Because you don't know the value. Remember, in a linear programming, you don't know the value of the decision variable. Okay, so your goal is to find the decision variable x1, x2, x3. Your goal is to find it. Okay, and then substitute it into the objective function and then get there. Now, and most of the time, if you can remember, in a linear programming, the decision variables are in the objective function and also they are in the constraint. So you can see that the phi, the lambda here is in the constraint, but also we're looking for it in the objective. And also the phi here is in the constraint, but is also in the objective. So our goal is to find the lambda. Now, the linear programming is designed in such a way that they will automatically find the lambda for you. And once you have the lambda, you can find the phi, okay, using the principle of change of subject. Okay, you can find it. So what is a lambda? Is a weight, is importance, is a weight, is importance, is a weight, is importance attached to each of the inputs in determining the efficiency. We'll be taking a couple of examples for you to get it. Okay. So what is a weight attached to the this very input I for firm J. What is the weight attached to it? The lambda will tell you the weight, okay, as far as that DMU is concerned. So if I am doing the efficiency of a particular DMU, it is subject to the constraint that all DMUs, if I should sum them, weight and sum them, they will not be less than, they will be less than or equal to the input of the DMU I'm assessing. Now, this is the input of the firm you are assessing. This is the target DMU's input. This is the target. That's why you have the 0. The 0 here is indicating the target DMU. The 0 is indicating the target DMU. And this 0 here is also indicating the target DMU's input. And this is indicating the target DMU's output. So that is why you have I0, R0. Now, they are also part of the left-hand side of the constraint, but they are the focus. They are the ones whose efficiency you are assessing. Now, Dinah explained that because we are dealing with output orientation, the phi must always be attached to the output. If we are dealing with input orientation, the theta will be attached to the input. The constraints will all remain the same. All the constraints here will remain the same, but you just move the phi and change it to theta and give it to x here for it to become an input-oriented model. Okay. Now, the left-hand side of the equation here is the technology set. Okay, so look at it. The left-hand side here is the technology set of the input. So the entire technology set, okay, is what you see, which is inclusive of the space plus the boundary of the technology. When I say the space plus the boundary of the technology, you should understand. I'll give you an example. Okay, so for example, if you look here, this whole space there, okay, is the technology, which includes both the boundary plus the space itself. This is it. This whole kuza manya thing, this is the left-hand side of the equation that you saw. That is the left-hand side of the equation that you are seeing right here. Okay. And that is what you see. So that one is always constant. What is changing? And then this xi0 is a target which is inside. It is a DMU you are trying to evaluate its efficiency, and it is part of the technology. And if it is part of the technology and is an input, then you want it to be, if it is equal to, if this summation has been equal to the value, it means that this DMU with its input is on the frontier. If it is equal to, it means it's on the frontier. It's on the frontier. But if it is less than, then it means that it's inside the frontier. If it is less than, then it is inside the frontier. And then let's go to the DRS constraint that she talks about. We'll come back to the details of this constraint. But the key point is this. The weight, they can be allowed to rise infinitely. And when you're allowing the weight to rise infinitely, then we are in the world of constant. You see, when something is rising infinitely, permanently, consistently, then it becomes constantly going. And that's constant returns. Now, the variable returns to scale simply assumes that size matters. Now, the constant returns to scales assumes that size doesn't matter. It assumes that all firms are of the same size. Okay? All firms are of the same size. That's what it assumes. Just a second. All right, let's box on. So size matters. Now, when we say size matters, it means that there are some firms that have got similar size as different sizes. Some are smaller size, some are middle sizes, some are bigger sizes. Now, if you have an industry that is like that, then you have to assume that there's variability, there's variable returns. But where you have the same kind of size, not exactly, but the same kind of size, like in the robotic industry, in the manufacturing firm industry, size is kind of constant. So the firms are of the similar size. Now, again, there's a question of what defines size, whether you are using the total asset or the fixed asset or what. But when there's that belief that, look, among the banks, the size, let's assume that we are measuring size by total asset. If you are measuring size by total asset, which is usually what they do, the literature does. If you believe that size matters, in other words, if you believe that when a bank is bigger, it can affect how it behaves, and when it is smaller, it can affect how it behaves, then you have to use the VRS. That is when you have to use this constraint VRS. But if you don't believe that size is really making an impact in the industry, then you eliminate this constraint, because this constraint says that size matters. So the weight must equal 1. But if you don't say the weight is equaling 1, the weighted sum of the weight, the importance attached to the DMUs, if it is not equaling 1, then you're allowing them to be equaling anything, which means they can be infinitely large. So the weights are just allowing to expand. And that is the constant retention scale. So this assumption is only predicated by what you know in the industry. But guys, listen, you will not be able to know whether VRS is operating or CRS is operating unless you test it. Unless you test it. That is why all of you will have to do that test. It's called testing the property of retention scale. We call it the scale elasticity at the industry level. I'm sure you all remember that in your proposals, you have to test whether the industry is exhibiting CRS or VRS. If you can test whether the industry is exhibiting CRS, and you have to test, and there's a test we use, which is called Semmer and Wilson test, non-parametric test of retention scale. I'll teach you that separately, okay? Once you're able to establish that. As for this last one, the non-negativity constraint, you know it, lambda J, okay? So the weight attached to every firm, the J is for the firm, the weight attached to every firm must be non-negative. You have to be writing some of these points down so that when you are explaining it to experts, you are not fumbled at all. So this is the main DEA model, envelopment model that you'll be using. That's why I'm concentrating a lot of my attention on it, so that you can fully get it. Any question? Any question on this? It's a very, very crucial model. Okay, so when you write it down next time, you should be able to, explain it in toto to anybody who will ask of you. Of course, some of the explanations are here. For example, the inputs and the outputs of the target DMU has been given. This is score. A 5-star is the output-oriented score. When it is equal to 1, it means that the firm is efficient, is on the frontier. When it's greater than 1, it means the firm is inefficient. And please note, in an output orientation, inefficient firms, the score is greater than 1. Output orientation. Inefficient, the score is, the 5 is greater than 1. But in an input orientation, the theta is less than 1 for inefficient firms. Note that in an input orientation, the theta is less than 1 for inefficient firms. And of course, the theta is equal to 1 for efficient firms. So whether it's input orientation or output orientation, the theta or the phi is equal to 1 for efficient firms. It's equal to 1 for efficient firms. But if it is input oriented, the theta is less than 1. And if it is output oriented, the phi is greater than 1. Okay? Now, so the interpretation of everything we said about a linear programming is what has been written here. Just read it and understand it. Now, let's talk quickly about a constant retention scale and then the variable retention scale again.
Okay.
All right, go ahead.
Okay, Doc, please, I want to draw us back to the envelopment, the model. And
let me just show you the model. Let me ask a question.
Yes, please. And please, you said the summation for the first line, the first constraint, said the summation of the weight and the input must be less than that of the target firm. And please, what does that mean practically? Like, why is it so?
Okay. So the input of a particular firm that you see here, the input of a particular firm that you see here. So look at this XI naught is a target, is not a target, is an actual input of a particular firm you are trying to assess its efficiency. So let's say a particular firm, say firm A, and that firm A, this is its current input. And this YR naught here is a current output. Are you with me so far?
Yes, please.
All right. Now, this current input, you want to know, you see, when it comes to input, you don't want to use more input. To be efficient, you want to use less input, isn't it?
Yes, please.
Any firm that wants to be good, you lose less input, and then you normally want to get more output from the less input. So if I can employ less resources and still get more output, I'm efficient. So because you are expecting to use less of the input and not more of the input, what you are saying is that but you see, in natural sense, it's not possible that you are always going to be using less of the input. Because one of the assumptions we establish is monotonicity, free disposability of input and output. In other words, it is possible that a particular firm in the industry will not look good. Do you know that? You can't
Yes,
say
please.
all of them are going to be efficient.
Yeah.
It's possible that some of them will not be efficient. Okay, now, so if you can see, this is the weighted input of all the other firms. Weighted input. And the weighted input of all the other firms, this weighted input you are seeing here is imaginary. It's imaginary. It's a production possibility. So the weighted input of all the other firms must be less than the input of the firm you are considering. It must be less. It must be less. It must be less. The weighted input, the imaginary firm's input must be less. Now, if it is less than your input, okay, so let's assume that somebody's input is less than your input, then it means that you are what? Efficient or inefficient?
Inefficient.
Exactly. It means that you are inefficient. Okay. So if there is an imaginary input that is less than your input, then you are inefficient. But you want to be efficient. So you would expect that the imaginary combined weighted input is equal to.
Okay.
So that is why you see both less than and equal to. If it is equal to, then it means that you are what? Efficient.
Efficient. Okay.
But if that imaginary guy's input is less than yours, then you are inefficient.
Okay. Okay.
Now, when it goes to the output, it's not less than or equal to, it's rather greater than or equal to, which means that the imaginary guy's weighted output, if it is greater than your output, remember the output, you want it to be more, but somebody's weighted output is more than yours, then it means you are what?
Yeah, inefficient.
You are inefficient. That is what it means. It means that you are inefficient because somebody is producing more than you are producing.
Yeah.
But if that hypothetical firm's output is equal to yours, that is when we say you are efficient. So
Thank you very much.
So the constraint is saying that make sure that your input you are having and your output you are having are at least equal to that of the imaginary, the hypothetical, the weighted hypothetical. Is it clear?
Yes, it is.
Good.
Thank you
So
very
that
much.
is how it goes. Now let's go to the scale efficiency. And I want you to pay attention here because you'll be doing scale efficiency. Now, should we use VRS or we use CRS? You've gotten a fair idea about it, but I want you to understand the terminologies. The people who pioneered the DEA model, they began with a constant returns to scale assumption. They assumed that all the firms were operating at the same optimal scale size. In other words, they assumed that all firms were of equal size. Is that realistic in real life?
No.
No. Because when you look at real life, are all the banks of the same size?
No,
No,
please.
please.
No. If you look at the size of Ghana Commercial Bank and the size of Fidelity Bank, Ghana Commercial Bank is big. If you look at even the branches, it's big. It's covered almost the entire country. Some of the banks have not gone into the hinterlands at all. They don't even know what's happening in Navrongo, in the border of Burkina Faso, in Savulugumanton. They don't know. The size is small. The scale size, the size of the total asset is small. The branches are small. These are some of the ways you measure size, by the way. And what can make some banks be smaller and some banks be bigger? One of them has to do with imperfect competition. You see, when competition is not perfect, if you can remember, the principle of perfect competition says that the firms are all of similar size, isn't it?
Yes, please.
That's what perfect competition, okay? One size fits all. That's perfect competition. They will tell you that firms are price takers. They are price takers. But life is not all about perfect competition. Life is not that perfect. There's imperfect competition. There are some firms which are monopolistic in nature, oligopolistic in nature, and all that. That can cause some firms to be smaller than others. Also, government regulations. You see, the government can bring a regulation that will force some firms to exit even the marketplace. For example, the minimum capital requirement. You can say that if you don't have a minimum capital requirement of $100 million, you can't operate. Financial constraints. Some of the firms have financial constraints. Okay, they don't have the finance. If you look at banks like EcoBank, they are able to penetrate, okay, innovative. And all of these will cause some firms, some DMUs, to be not operating at the optimal scale. Does it make sense? And that is why you have to go beyond constant to variable. So in 1984, okay, about 6 years later, Banker joined the group. When Rhodes has exited the group, Banker, Chance, and Cooper came and developed a variable returns to scale. Okay? Because in real life, most services organizations tilt towards that VRS. And that is the whole idea. But you have to test for the return to scale underlying the technology. You have to test it econometrically. You have to test it using bootstrapping. You have to test it using other means. You can use other non-parametric means, okay? And you have to test it, and we'll do that. Then you can say that, oh, as for my industry, this is what is operating. Once you can do that, that is fine. However, using the principle of this returns to scale, you can identify something very important. And I want you to pay more attention to what I'm about to share with you at this stage. Now, listen carefully to what I'm about to say because it's very important. Do you all see the graph on the bottom right? Do you all see this graph?
Yes, Doc.
Okay. Now, if you look at the vertical line, from O to C and upward. You all see O to C and upward. O to C and upward. Do you see that?
Yes, Doc.
Yes,
Yes, Doc.
That is the constant returns. Now, remember, this is an output on the top vertical and input on the horizontal. Constant returns says that if you move, remember that line OC is a 45-degree line. Actually, I can spend a whole hour on this graph, on this slide. Okay. And when you increase the output, say from points here to there, when you increase the input from that point to any point on this section, what's going to happen is that the output is going to double. Okay, I'll use a new graph to explain what I mean to you because this is critical. This is important. Okay, so let's look at this graph here. Okay. You have input here, X, and you have output there, Y. And you have this 45-degree line. This is a constant returns to scale graph. Now let's assume that you have an input here called 1, and then it is producing an output here, say 3. And then you move to this point, say an input here called 3. Okay, you move this distance. When you trace this distance up until it hits the graph, you will expect that the output will go somewhere like 6. Do you agree with that?
Yes, Doc.
Now that is constant. So what we've done here is that we have increased the output by, say, 150%. Sorry, we have increased the input by 150%, and the output is also increasing by maybe about 100%. Yes, about 100%. Okay, so each time we increase this one by 150%, this one will increase by about 100%. Okay, I could choose to call this one 2 so that it makes it sensible to you. I can increase the output by 100%, increase the input by 100%, the output will increase by 100%. Okay, so this 100%, and then this one also goes up by 100%. Now, what does that tell you? It tells you that when you double the input, the output is doubling. When you triple the inputs, the output is tripling along the constant returns to scale graph, because it is a 45-degree line and it is giving half of the whole thing. Okay, it's giving half. And that is what you saw in the graph. But then the variable returns to scale comes, and then it says that no, life is not all that constant. It doesn't even start from the origin. It starts somewhere here, it goes through there, and then it continues here. Okay, so this becomes the variable returns to scale graph. And so if you look at this graph, let me use a different color to do that. If you look at this graph is not constant. Do you realize that? Along the line here, along the line for the first one, the one on the origin, the constant returns to scale graph is constant. Everything from the x-axis will reflect on the y-axis. But when you're on this line, it's not constant. It's not constant. See, here, if you increase the input, even if you're on this section there, then you increase the input, the output is not even going to. Even if you don't increase the input, the output is increasing on this line because it's vertical. It's vertical. Okay. So even if you are at 1 and you have not increased, and then we are somewhere here, you are at 1 and we are somewhere there, and then you don't even increase the 1 to 2, you see, the output will still increase. You don't even increase, you are still at 1, the output will still increase to that. So you can see that at this section, and then when you are at this section here, as you increase the output, the input by small, the output is increasing. As you move along the red line, is increasing, but at a decreasing rate, until you reach this section. Now you increase the input by small margin, okay, or by big margin, and the output will still be increasing by small. So here it was increasing by big. Here it's increasing by average, but as you move on, so that's the variability. That's the variability that we are talking about. Now, the question is this. This variability is as a result of the nature of the graph. So look at the graph carefully. So when you look at the graph, look at the firm at point A. Look at the firm at point A. Okay, that firm is having the input you see, and the output produced is at L. Now, watch carefully. If you measure the output or output efficiency of firm A, you'll be using the DRS graph. If you measure the output efficiency of firm M, actually it's the same firm A, but it's now firm M. You'll be using the constant returns to scale graph. And the principle between the constant returns to scale and the variable returns to scale can even help us to generate what is known as scale efficiency. Scale efficiency. So look at the top there. Technical efficiency when measured relative to the CRS, the cone, we call it the conical hull. Okay, but when you look at that cone, it looks like a cone. Okay, and then the VRS looks like a convex thing. So sometimes you call it a convex hull. So technical efficiency measured according to the conical hull, the CRS, is equal to the technical efficiency measured according to the VRS times the scale efficiency. Now, using the principle of change of subject, you can find the scale efficiency to be technical efficiency CRS divided by technical efficiency VRS, which is on the far right here. Do you see what I'm seeing?
Yes.
All right. So now listen. If a firm is efficient under the VRS, we say the firm is BCC efficient under the VRS. And if a firm is efficient under the CRS, we call it CCR efficient, because the people that brought it was Chance Cooper and Road, CCR efficient. Now, look at the firm at A. A is efficient at the VRS because it's on the frontier. Look at A. A is efficient at the frontier. Now, A is exhibiting something we call increasing returns to scale. Now, why is that so? Why do we say so? Because at the point of A, look at it. Even if you have not increased the input, okay, output is increasing. So let's say that we are at point below A, and you have not even increased the input, output will increase to the point A, and output is good. So output, any firm within this region is exhibiting increasing returns to scale. It is similar to the principle of marginal returns, okay? The principle of marginal return. But this has to do more with the scale. Scale is more of a long-term phenomenon than marginal return, which has to do with more of a short-term phenomenon. So this firm is exhibiting that. So how do we calculate its scale efficiency? It's simple. If you want to calculate the scale efficiency of firm A, okay, all you have to do is to measure the efficiency of firm A relative to the frontier. Now, how do you do that? Look at the distance. The way you measure the efficiency, the technique, the VRS, because it's on the VRS. If you want to measure the VRS, you move from the distance here. Is the distance to the frontier divided by the distance to the firm. And actually, the firm is also on the frontier. So it will be LA divided by LA. Okay, LA divided by LA. Write it down, write some of these things down. Okay, LA divided by LA will give you 1. So it means that the VRS score for firm A is 1. Okay. Now, this same firm A, okay, now if we were to measure the CRS score for firm A, the CRS score, okay, for firm A, it will be the distance to the frontier, which is where M is. So it will be LM, the distance to the frontier, LM, divided by the distance to the firm, which is LA. Now, whilst this might be a little bit confusing, let me just show you here. Okay, so for VRS, so technical efficiency, VRS, okay, for firm A, okay, this is going to be the distance to the frontier, which is LA divided by LA. Okay, that was 1 because it was on the frontier. Now, the same technical efficiency, but this time related to the CRS, is always defined as the distance to the frontier, and that frontier point was M. So it will be LM divided by the distance to the firm, which is LA. Now that one, we know is going to be less than 1. How do we know? Because we know that the distance, the LM is shorter distance. Okay, LM is shorter distance. Now, how do we know that LM is shorter distance? Well, look at the thing. Look at the LM here. LM there is shorter than LA. Okay. Now, the difference between these two will give us the scale efficiency. Now, watch it. Watch how we calculate the scale efficiency from this. Scale efficiency, okay, is given by the technical efficiency of the CRS divided by the technical efficiency of the VRS. Okay. Now, what is the technical efficiency of the CRS? Okay. It is LM over LA. So let's write that. LM over LA. And that is divided by, okay, course, if it is divided by, it's divided by its VRS. And remember, divided by is always, you can do multiplied and then swap the denominator and the numerator. So we can say multiplied by LA over LA. Now, LA will cancel LA, and we are left with what? LM over LA, which is the scale efficiency. Now come here, and then now look at the thing. So you can see that the scale efficiency here is given by LM over LA. LM over LA, which of course is less than 1. Okay, which is less than 1. And that shows that the firm is not constant returns. So when you look at a firm like firm A, that firm is exhibiting increasing returns. So when the scale efficiency is less than 1, okay, it simply means that that firm is exhibiting, increasing returns to scale. However, if you look at firm B like this, look at firm B and firm C, you see, because the CRS line and the VRS line are all meeting at the same gap, because they are all meeting at the same gap, you can see that the scale efficiency is going to be the same for both of them. And therefore, any point between B and C is exhibiting constant returns to scale. We call them firms operating at the most productive scale size. That is what you see MPSs. Firms operating at the most productive scale size, B and C. So B and C are the firms operating at the most productive scale size, which means they are exhibiting scale efficiency equal to 1. Okay. Now, look at for firm E. It's very interesting. It's not on the line. It is not on the line, but it can exhibit scale efficiency of equal to 1. Go and use the principle. It will be, if you have to calculate the constant returns for E, okay, constant returns for E will be PQ divided by P. PQ divided by P. Remember, I'm looking at the constant returns to scale line. And then for variable returns to scale, if you are calculating the variable returns, technical efficiency, variable returns for E, is going to be PR over PE. So the first one is PQ over PE. And then you have PR over PE. See, this is calculated on your left here. So PQ over PE, okay? And then you have PR over PE divided by, but when I swap it, you get PE over PR. So when you actually cancel the PE and the PE, you are going to get PQ over PR. So PQ divided by PR is actually the scale efficiency for E. And that is also equal to what? Equal to 1. Okay? So it means that that firm is exhibiting things. So using these two graphs of constant returns and variable returns, you can beautifully execute the scale efficiency of every firm. Some of you are doing scale efficiency at the firm level. Is that correct? Is that correct?
Yes, please.
That's how you're going to calculate it. This is how you're going to calculate it. Okay. The software will calculate all of these things for you, but you need to understand what is behind the software. That is how, so it's going to calculate the scale efficiency at the firm level for every one of them, and you will know which one is operating at increasing returns, decreasing returns, constant returns, and then you will know that, oh, this number of firms are exhibiting this. By the way, when a firm is operating at decreasing returns, it means that a firm is getting too large. Okay, so that firm can merge with a firm exhibiting increasing returns. So decreasing returns firms can merge with increasing return firms. This is where policy becomes interesting. Okay, so if you happen to see a lot of decreasing returns to scale, DRS, and IRS, one of your recommendations would be that there's a possibility of measures in the industry. Okay, there is a possibility of measures in the industry. And these are some of the things that you can recommend at that point. Now, mathematically, you can model all of this. Everything we did here is graph. You can model all of this mathematically. It's very simple. That VRS constraint, you all remember. You remember we had a VRS constraint, which was the weighted sum of the the lambdas should be equal to 1. That weight, if we change it and say it shouldn't be equal to 1, remember under the CRS, you don't even bring that last constraint. Okay. So you can determine scale economies by bringing something we call non-increasing returns to scale constraint. This one is a very simple thing. When we come to the calculation, you know, okay, it's just a matter of clicking and telling the command to change. So when you change it to that, if you add this constraint instead of that constraint, if you add the NIRS instead of the VRS, you will now have this non-increasing returns to scale constraint. And what's going to happen? What's going to happen is that you can now determine the scale efficiency of all the firms. So when the technical efficiency score for the CRS equals that of the VRS, then we have constant returns. If not, then we compare the VRS with the NIRS. Now when you compare and they are the same, then the firm is exhibiting decreasing. If they are not the same, then the firm is exhibiting increasing returns. But you see, the good thing about the software you'll be using is that that software will be doing all of this for you. But you need to understand what is really happening there. Any question? Now, one quick thing about this efficiency at the local level, increasing returns, constant return, decreasing return. Now, a quick point: if the IRS holds at a Pareto efficient point, if the IRS holds at a Pareto efficient point, it means that if you raise the input, and this we are talking about increasing return. You see, the word increasing should guide you. It means that if you should increase the input by a small percentage, the output will increase by even bigger. That's what we mean by increasing returns. If you increase the input by small or tiny, the output will move, boom, 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 boom. That is increasing returns. Okay. So, and of course, the opposite is decreasing returns. So if you want to determine these local returns, increasing, decreasing, constant, if you want to do it at the DMU level, not at the industry level. And the industry level, you don't bring the NIRS into the picture. You just do CRS versus VRS. Okay. But if you want to really, really, really do it at the DMU level, this is good because it's for managerial policy purposes. And I just spoke to you about measures and acquisition. Okay. You can use that. If the firm is operating at the most productive scale size, we say that the firm is exhibiting constant returns to scale. And you will see some firms like that in your industry. Of course, we've spoken about the other types of returns to scale, which is the NIRS and NDRS. All of them are not too important, but when you want to dig deeper into the local return, then you can consider this thing. Now, one last point to note, that the result secured will depend on whether you are dealing with input orientation or output orientation. And this is a clue, take this, okay? That IRS, increasing returns to scale, will usually come from input-oriented model. So when you are doing an input orientation, you are more likely to get increasing returns to scale, okay? Whereas if you have chosen output-oriented model, you are more likely to be seeing decreasing returns to scale in most of your data. So it is orientation based. It's orientation based. So if you are using output orientation and you are seeing a lot of decreasing returns to scale, don't be worried. It's because of the orientation you are using. Okay. But if you are doing non-orientation, then that one you are more likely to see both or all in there. Okay, so this is the summary. I should normally ask you this question. If you look at these 5 DMUs, look at them, A, B, C, D, okay, A, B, C, D, and then H. The H, you have it in 3 corners. You have H prime, and you have H prime. Look at it carefully. Assume that 5 DMUs A, B, C, D, E, and H in the figure. If you look at the line OBC, OBC is a constant returns to scale frontier. We've already established that. And then the variable returns to scale frontier is AB, BC, and CD. AB, BC, and CD. That is a BCC frontier. Okay. And if you look at it, that A, B, B, C, and C, D, it is exhibiting IRS, CRS, and DRS. So all the firms, if you scatter plot your firm, all the firms down here will be exhibiting IRS. All the firm on the line, or even in the domain around the line, will be exhibiting CRS. And all the firms after C, on the line of CD, up or down, will be exhibiting that. Now, let me tell you what is funny. Let me tell you what's funny. What is funny is this. If you look at, I like this because this is interesting. If you look at H, look at H. If I were to do input orientation, I will move to the left. If I were to do input orientation, I will move to the left until H becomes H prime. And the moment it becomes H prime, then it means the returns to scale at that local level will be IRS. You realize that? But if I should choose output orientation, I'll go vertically up. And I'll hit the frontier between C and D. And H prime prime is in the domain of what? Decreasing returns. So you can see that the type of orientation here is affecting the returns to scale or the local returns to scale for that particular firm H. So if I'm at H, the kind of orientation I choose will indicate whether H is exhibiting DRS or exhibiting IRS. So that is why we said that orientation matter here. Okay. And remember, for those of you who don't know, input orientation is when you are moving on the left in an input-output framework, when you're moving on the left. And output orientation is when you're moving on the top, on the vertical top. Okay, so that is a key point. So I like this. So on the line AB, IRS prevailed. This is what I just said, to the left of the B, for the BCC model. And on the line CD, DRS prevailed to the right. What I just said here. Okay. Now, if we estimate the VRS local returns for H, if you look at it for H, and we choose VRS model, okay, using the input orientation, it will exhibit IRS, but output orientation will exhibit DRS at H, which is exactly the point that I just said. And now these two graphs will just show how the non-increasing and non-decreasing returns to scale look like. We don't normally talk about this separately because they are embedded inside this. They are all embedded inside this. If you look at this non-increasing, it is embedded inside this here. It's embedded inside it. This is the last slide we are looking at. It's embedded inside this. But when you're looking at the non-decreasing, this one, you see that one doesn't start from the origin. It starts away from the origin. That is non-decreasing. It's non-decreasing, so it's always increasing more or less. Okay. And that one can be found inside this angle here. Okay. So it's like taking from A, B, C upward, going all the way up. And that is how you are able to get the final situation. Ladies and gentlemen, that brings us into the end of this nitty-gritties related to the sort of returns to scale before we go into the practicalities. Any question at this stage?
Presentation, you said that when you test at RTS at the firm level, it will help you to determine those firms, those that are operating under decreasing and then those operating under increasing return to scale. And such results can inform decisions such as merging. Okay. I want to find out at the cross-country level, is the estimation or this test at the firm level also important, and what decisions can be taken?
Oh yeah, you are talking for your research.
Yes, I am looking at it from my point.
Yeah, you should just look at what other studies have done. First of all, if you are doing something at the country level in energy, okay, and you're looking at the energy sector of, say, Ghana versus US, and Ghana is exhibiting DRS, US is exhibiting IRS. Okay.
Yes.
What it means is that sometimes we can come together and formulate energy policies that can positively affect both of us. so that we are able to generate more energy, because you are energy interdependent. See, you can produce a lot of energy, doesn't mean that you'll be using all of that energy.
Okay.
Other people will be needing that energy from you. So, and then also your energy production can also affect the environment, which can affect our environment, because we can be in borderlines, and your energy production will go into the atmosphere. Okay, the wind will take those gaseous substances and to another country. So depending on your size, your productive or non-productive skill size, you will now be able to identify that certain policies have to be done in such a way that we all benefit equally from the production of that particular energy. So yes, there is a possibility of that putting our resources together. Not necessarily exactly merging, but putting our resources together. That will enhance the pollutants that will probably come from the production of energy. Because if your pollution is in Nigeria and I am in Ghana and we are close, and then your pollution, the production of oil is affecting me, or your energy production is affecting my environment, you can't say that we don't have to come together to decide on something. You get what I mean?
Yes, Doc.
Yeah. So if you're producing some intercontinental ballistic missiles, when you fire the missiles from here, from Iraq to the United States, it doesn't mean that some particles will not be springing from the neighboring countries. So we have to come together. That coming together is a form of policy that have to be done by both countries. So yes, there are possibilities of policy orientations.
Okay. Thank you, Doc.
All right. Any other question? You are going to create your own kind of hypothetical artificial data, create your own data, plot it, scatter plot it, see where they are located, and then do your examples and calculate the return to scale for each one of them. You can hand calculate. No, so that in the big data set, the software will do full calculation for you. And this is very important. So next time we are going to use this. So go and type this data into Excel exactly as it is. Exactly as it is. Type this data into Excel, because we are going to use this data, which you would have typed already into Excel, and we are going to work with this data next time and take it through everything. This is the data we are going to use for all that we have done, summarizing it, using details of it, and then expanding it to estimating the Manquist productivity index, and even going forward using this same data to calculate, cost productivity, using this data to calculate cost productivity, cost affordability, and all of those things. And then it appears that you have to change your affordability thing, So
okay, Doc, I'll contact you.
All of these things, go and type this data as it is. Type this data and scatter plot the first one, the white space one. Scatter plot it, because you're going to use it. Okay. And that's important.